See this problem. A magnetic field setup using Helmholtz coils is uniform in a small region and has a magnitude of 0.75 Tesla. In the same region, a uniform electrostatic field is maintained in a direction normal to the common axis of the coils. A narrow beam of charged particles, all accelerated through 15 kilovolts, enters this region in a direction perpendicular to both the axes of the coils and the electrostatic field. If the beam remains undeflected when the electrostatic field is 9 into 10 to the power of minus 5 volt per meter, make a simple guess as to what the beam contains. Why is the answer not unique? In this problem, we have an error, that is this electrostatic field value 9 into 10 to the power of minus 5 volt per meter. If you use this value, we won't reach the answer that is described in the textbook. So according to textbook, we need to follow. So if we use 9 into 10 to the power of 5 volt per meter, then we will reach the exact answer which is given in the textbook. Our motive is, there are two coils. So in these two coils, current is flowing so that they will have some magnetic field. So that magnetic field will remain as uniform between those two coils. Because they are nearer and the flowing current is also the same in magnitude and same in direction. So there exists a uniform magnetic field between these coils. Such type of coils we call it as Helmholtz coils. That's what the given thing, Helmholtz coils. Now an electric field is set up such that it is perpendicular to the magnetic field like this. So these two are the electrical plates which are producing uniform electric field which is perpendicular to the magnetic field. So here assume that the magnetic field is in x direction and electric field is in y direction. These two are perpendicular to each other. Now we are sending some charged particles which are accelerating from a device towards this such that the direction of the particles is perpendicular to this plane, like for example in z axis. So x, y, z are mutually perpendicular. Like here also the magnetic field is acting in one direction, electric field is acting in one direction, and particles are moving inside that field such that it is perpendicular to those two directions, like a xyz axis. And also given that this beam is not deflecting due to this electric and magnetic fields. The electric and magnetic field is set like that the forces should be equal. For example, the force of magnetic field on the charge is equal to the force of electrical charge, such that it won't give impact on that beam. So this is the given condition. We need to find out that particles which are moving into that field. That is our motive. And along with that, we need to prove that the answer is not unique. That means some other particles also can move like that under these given conditions. Now let's move to investigation part. The magnetic field given is B is equal to 0.75 Tesla, and electric field is given as E is equal to 9 into 10 to the power of 5 volt per meter. So given thing is minus 5, but it has some error, so that we are considering 9 into 10 to the power of 5 volt per meter. And the potential which is accelerating the beam V is equal to 15 kilovolts, or I can write like 15 into 10 to the power of 3 volts. Now come to the resolving part. We came to a condition that the force of magnetic field which is deflecting the electrons or charged particles which are coming into the field is balanced by the force due to electric field. So I can write like FB is equal to FE, but FB is BeV, where V is the velocity of the electron, which is equal to E into E. This is the force by the electric field. So EE gets cancelled, so that implies V is equal to E by B. Now the charged particles are accelerated due to some potentials. So due to that potential, it is gaining some kinetic energy. So that kinetic energy half mv square is equal to, it is due to potential, so I can write like E into V. E is the charge and V is the potential. So on a whole, we will consider as electrical energy, which is similar to the kinetic energy gained by the charged particles. Now I am taking E by m, that is equal to V square by 2V. We got V, so that is E square by 2V B square. So this is E by m value of that charged particles which are entering into the magnetic field B and electric field E. Why we are considering E by m? That is conceptual thing. So the particles are charged particles, so they must have charge Q. Those are particles, so they must have mass. Using these two, I can guess that particles. So that I am considering this E by m ratio. So from the given things, E is 9 into 10 to the power of 5 into 9 into 10 to the power of 5 because it is square, divided by 2 into 15 into 10 to the power of 3 into 0.75 into 0.75. I will remove the decimals and I will make the magnetic part into one term. 9 into 9 divided by 2 into 15 into 75 into 75 into, on the top you have 10 to the power of 5 and 10 to the power of 5, so 10 to the power of 10. Below you have 10 to the power of 3, so that will become minus 3 if you go to numerator, so 10 to the power of minus 3, and here you will get 10 to the power of minus 2 and another 10 to the power of minus 2, so 10 to the power of minus 4. If it goes to numerator, it will become positive, so it is plus 4. Now 3 3s are 9, 3 10s are 30, 3 1s are 3 25s are, 3 3s are 3 25s are. So on a whole you will get 3 by 25 into 25, and this 10 will become 10 to the power of 1 here. If it goes to numerator, it will become minus 1, so I can write another minus 1 here, so you will get 10 to the power of 10, that is equal to, so I am writing 300 into 10 to the power of 8 divided by 25 into 25. I am making simple calculations, so 25 ones and 25 12s. So another term like 1200 into 10 to the power of 6 I am taking by 25. So 25 ones, 28, 25, 48. That is equal to 48 into 10 to the power of 6 coulomb per kg is the E by m ratio of the given charged particles. We need to consider whether these are electrons or protons or some other nuclei. So first of all, I am taking the E by m ratio of electron, and I am taking E by m ratio of proton also to calculate, to compare with this value. So E by m ratio of electron, first of all I am considering E by m ratio of electron, which is equal to 1.6 into 10 to the power of minus 19 divided by 9.1 into 10 to the power of minus 31, that is equal to, you will get 0.17 into 10 to the power of 12, or else I can write 17 into 10 to the power of 10. If we compare these two terms, Ebm ratio of electron is far more than the given particle's Ebm ratio. So that means the particles are not electrons. We will check with the protons also. So proton has mass like 1837 times more than electron. So I can divide this value with 1837. 17 into 10 to the power of 10 divided by 1837. I'm taking 1700 into 10 to the power of 8 divided by 1837. So which leads to nearly 0.96 into 10 to the power of 8, or else 96 into 10 to the power of 6 coulomb per kg. So if you compare these two, this value is double than this. That means there is some relation between these particles and that protons. So the Ebm ratio of given particles is 48 into 10 to the power of 6 coulomb per kg, and the Ebm ratio of proton is equal to 96 into 10 to the power of 6 coulomb per kg. So it seems to be double than the given particles. That means there exists another massed particle which doesn't have charge. So proton, and assume that there is a particle which is a neutron, because neutron doesn't have charge. So if we consider this particle as 1, these particles Ebm ratio will be equal to the given particles Ebm ratio. So if a nucleus has one proton and neutron which doesn't have electron, so it will possess Ebm ratio as 48 into 10 to the power of 6 coulomb per kg. So from this I can guess that these are the particles which are projecting towards that fields. So what is this particle? For example, consider hydrogen. Hydrogen has one proton and one electron. If we take out that electron, it will only have proton, but the Ebm ratio of this proton will be similar to this. So that means it is not the exact particle. If we take deuteron, which is having one proton, one neutron and one electron. If we take out this electron, the remaining thing is one proton and neutron. So this will possess the Ebm ratio as the given particles Ebm ratio. So that means, can I say it as deuteron? Yes. So the particles are deuterons. And one more, helium. Helium has 2 protons, 2 neutrons, 2 electrons. If we take out these electrons, helium becomes He++. So He++ has 2 protons, 2 neutrons. So your charge become double and your particles also become double, but the ratio remains the same. So Ebm ratio of these helium++ will be same as the given particles Ebm ratio. That means we can say these particles are also helium++ ions. So we have two types of answers. One is deuteron and one is helium. Even lithium++, like 3+ also executes the same Ebm ratio. So like that, the answer is not a unique, but the particles which are going inside the field will be look like these types. You know, this is an experiment which is conducted by Thomson. Thomson is a scientist who found the existence of electron. When he is doing this type of experiment, he has accelerated some beamed particles towards the perpendicular fields. So he come to know that atom is divisible and electrons are those particles which is inside that atom. So that he came to plum pudding model. So this is the experiment he did. We worked on that problem to get the charged particles that are projected inside that perpendicular fields.